Yeah, moving.
In Glenview, high winds took down a power line, trapping a woman inside her car. Police did not know if the wire was live, so they ordered the woman to stay inside the car to avoid contact with the ground. Then they shut down the entire intersection. The driver was trapped for nearly 2 hours until a ComEd crew showed up.
I called the fire department and told her to stay in the car and not to move and not to attempt to get out of the car. So
how was she handling this?
Well, at first she was crying and she was pretty hysterical and she was talking to family members on her cell phone.
ComEd crews eventually shut off the power and the woman was allowed out of her car. The driver was a bit shaken, but she is said to be okay.
All right, so why was she okay inside the car? Despite the fact that there was a live wire on top of the car. Checking the inside as well as the outside of the metal. Now you have some idea as to why she's going to be okay as long as she's on the inside, right? She can touch the inside of the metal, she's fine. So the question is, if she's touching the outside of the metal while sitting on the inside, why is it that she's still fine? So that's something that we will discuss. So Bailey is correct. I mean, windows could be down. It makes no difference. She's not getting struck by lightning. The electricity is just on the outside, and she's going to be fine as long as she's on the inside, right? So the question is, why is she fine as long as she's on the inside, despite the fact that the car is part of the circuit? So we'll get back to it. All right, so the metal on your body, does it attract lightning?
Come on, please help me out. Yes, we'll carry you. Hold on. I got struck by lightning? Yes. How the fuck did that happen?
In August 2003, Matt Thompson was hit by lightning in the hills outside Keystone, Colorado.
A bolt of lightning taken straight in the chest.
It just came out of nowhere.
The direct hit traveled all the way through Matt's body.
I had no clue what happened.
Matt's story was big news. On websites worldwide, the issue was raging.
Hey, you almost died.
Was Matt's metal tongue stud the reason he was struck?
So my tongue ring. No, dude, you might have swallowed it. Let me see. Where's your tongue? Let's see it. Oh, it's broken off in there, it looks like.
Body jewelry attracting lightning strikes?
This is awesome. All right, let's do a quick review. All right, so what's flux? What's flux? What causes flux? All right, so what is flux?
Flow.
Okay, so flux means flow. All right, what's flowing in this case?
Electrons?
Okay, when you say electrons, you mean the electric field, right?
Yes.
All right, so in this case, what's flowing is the electric field. Up. Yeah. So the electric field is what's flowing in this case. All right, so what's flux? Flux means flow. What's flowing is the electric field through the area of a Gaussian surface that we're looking at. All right, so you got a charge emitting the electric field. So the charge is going to be responsible for the electric field. So this electric field being intercepted by a Gaussian surface, area of the Gaussian surface. So the green is the area of this Gaussian surface that you're looking at. This thing is three-dimensional. And notice that through the Gaussian surface, the electric field is just flowing out. So the definition is the electric field intercepted by the area of the Gaussian surface. All right, I'm not going to use the integral sign, so this is the total area. So phi or phi represents flux in this case. All right, so what causes flux is the next question. What causes flux is the net charge on the inside of the Gaussian surface. So the net charge on the inside of the Gaussian surface is this charge right here. All right, so symbol phi represents the amount of electric field intercepted by the area of the Gaussian. That's it. By definition, flow means electric field is flowing through this area. What causes it is the net charge on the inside. So here's your Gaussian region. And inside the Gaussian region, you have a net charge in this case. If the net charge is positive, you end up getting an outflow. So the flux is going to be positive. If it's a negative charge, you end up getting an inflow. In this case, the flux is going to be negative because the charge is negative. All right, this was a nice review. All right, going back. All right, so what's the electric field within the Gaussian surface if the net charge resides on the outside? All right, guys, if the net charge resides on the outside, so what is the flux of the Gaussian in this case? If the net charge on the outside, what happens to the net charge on the inside is going to be 0. So if the net charge is 0, the Gaussian, the flux is going to be 0. All right, that's it. So it's 0. Give yourself 2 points for that. All right, where does the extra charge reside on a metal? Extra charge, excess charge.
On the outside?
Okay, before we get back to that. So what's the net charge inside a Gaussian surface? If there's equal number of positive and negative charges on the inside. So if you have, it would be 0 as well. It would be 0 as well, right? If you have equal number of positive and negative charges, the net charge is going to be 0. All right, so if you have equal number of positive and negative charges, when you add them up, it's going to be 0. All right, so that's what happens. All right, so extra charge on a metal is going to reside right at the surface, right? Okay, so the question is why? Come up with a justification as to why the excess charge has to reside right at the surface. When we are dealing with excess charge, we are dealing with like charges, right? Like positive or negative charges. So if that's the case, what happens between the like charges?
You're going to repel each other, and the surface is going to be like as far away from each other as they can spread out, probably.
All right, so they will repel each other to the surface. and they will get repelled as far away from each other as possible, right? So surface is the furthest that they could get to. All right, so I'll give you 5 points for that one. All right, so we had a discussion about this. These are usually test questions because I want you to be able to justify these. So we're talking about commercial airplanes. On average, they get hit twice by lightning. So the passengers on the inside will remain safe. So why is it that the passengers on the inside will remain perfectly safe from the lightning?
Well,
all right. Okay, go ahead.
I'll say, well, the plane just like kind of acts as like it's a giant car, I guess you can say, with like the same weight how it protects. It's just like a car, but amplitude and size by like a couple like 100 times. So it's the same principle as why if you're safe in a car, you're safe in a plane, just a giant metal flying box. So.
All right, so I'm going to give you 5 points, Bailey. What I'm looking for, if this were a test question, and obviously it's going to be a test question because this is the sort of stuff I ask you guys, usually. Number one is a metallic enclosure, right? Okay, so a couple of things that I'm looking for. I may repeat some of the questions on every single test, but I'm repeating a question, which means that I'm also looking for something more than before. Okay, so let me get back to what it is that I'm looking for. So at least when you guys have this question on the test, you know how to answer. Number one, if it's a metallic enclosure, when lightning strikes, it's going to deposit same like charges onto the metallic enclosure. All right, I'm going to make this a metallic enclosure. This is your airplane or UFO or whatever. All right, so the lightning comes in and then boom, zoom, and then just zaps it. So imagine that the negative charges are being deposited. All right, so what happens to the negative charges, the like charges, like negative charges? Immediately they will be repelled to the surface. All right, so surface is going to become negative charge. Okay, this I'm going to indicate as a negative net charge. That's what you're looking at. So that negative net charge is going to get dispersed, distributed onto the surface. Okay. Okay, so once that's the case, because the like charge is the furthest that they can repel is going to be the surface. So the question is this: why would you be safe while you're on the inside? The reason why you're going to be safe on the inside is because of the lack of electric field on the inside, right? So how do we know that the electric field on the inside is going to be zero? We know that because what I'm going to do is I'm going to place my Gaussian right here. All right, so blue is going to be my Gaussian, right where the surface is, right inside the surface of the metal. And then what we will do is we're going to take a look at the electric field on the inside. All right, so flux, that's the amount of electric field intercepted by this area. So I'm looking at the area of this Gaussian. It depends on the net charge on the inside, right? All right, so solve for E. When you solve for E, there's the expression that you come up with. Okay, cool. So this represents the net charge on the inside. And what is the net charge on the inside? Net charge on the inside is going to be zero, right? All right, because the net charge on the inside is zero, the electric field on the inside is going to be zero. Okay, so what does that mean? What that means is if the electric field on the inside is zero, which it is, all right, and your body has charges on it, obviously. Okay, so the absence of the electric field, there would be no force acting on the charges making up your body. All right, there's no way you could get electrocuted under the circumstances because the net electric field is zero means that the charges on your body will not accelerate through your body. That's what it means. Okay, so you're going to be perfectly safe. So I'm looking for two explanations from the previous test. I didn't get a chance to grade the previous test yet, the conceptual portion. All right, everything is graded out of 2 points. Okay, so the reason why you would be safe in the previous test because the light charges will be repelled to the surface, so that's the full explanation. And they would remain at the surface. While you're on the inside, there's no way for these charges to be able to get inside of the metal. But the second explanation is, and that's the explanation I'm looking for, because this is a metallic enclosure, and inside the metallic enclosure, the electric field is going to be zero. The reason why the electric field is going to be zero because the net charge inside is going to be zero. All right, so that's the explanation I'm looking for, or I will be looking for, more like it, on the test. All right, so number 6 is taken care of. Or for the exact same reason, the person inside the car. Okay, so this is in regards to the car. The woman gets trapped inside a car. So there's a down power line remains in contact with the metal casing of the car, which means that the metal casing of the car is already part of the circuit. If you walk up to this car and put your hand on it, it more than likely it will kill you. All right, it's a dangerous situation. So she's inside the car, she's touching the metal inside. She can also touch the metal on the outside. So the question is, why is she safe? Guys, she's going to be safe for exactly the same reason, believe it or not. What is the net electric field on the inside? All right, so the current is composed of like charges, electrons. So they will remain outside of the car. All right, despite the fact that she's on the inside, the electric field on the inside is zero. Got it? She can touch the metal on the outside. None of these charges will be forced to go through her body. That's the reason why she can touch the inside. She's fine. She can touch the outside of the metal. She's still fine. That would be the short answer. All right, but there is a little bit more to it than that we will discuss. So this is more of a setup for the next lecture. So she can touch the inside of the metal. She's fine. Because the electric field, there's no net electric field on the inside. So there's no electrostatic force field on the inside that would push the charges through her body. All right, so, okay, now that we've been discussing it for a while, for the past 5 minutes, what is the strength of the electric field inside a conductor? And explain why. Why the strength of the electric field inside a conductor is going to be zero because the net charge within it is zero. The net charge would reside outside, not inside, because the net charge of like charges would be repelled to the surface. And inside a conductor, the net charge has to be zero. because the charges are free to move, and the furthest that they're going to be able to move is to the surface of the metal. All right, so that's it.
That
So,
why the air is
go
that-
ahead.
Is that why if you open the window, that's a problem? Because the air is charged and it charges the air inside your car, and then it wants to flow through you. Is that why that's an issue?
Matthew, are we talking about lightning?
Yeah.
Okay, just hold that thought briefly.
Okay.
No, that's not the reason why, but that's it. Good enough. I like the way you're looking at it. Hold on. Let's discuss this shortly. All right, so what's the strength of the electric field on the inside? It's going to be 0, so we're good with it. Okay, going back to what Matthew was saying. Matthew, give yourself 5 points. What's the best place to be during a lightning storm? I would take a metallic enclosure over just about anything else, 100% of the time. I would much rather be inside an airplane or inside a car, and with my windows up. Okay, so the question that Matthew is asking is a good one. Why is it that you have to have your windows up? Okay, this would be a nice test question, actually. Now that I'm thinking about it. You need to have your windows up, and here's the reason why. Lightning phenomenon. Let's get back to it. All right, so bottom of the clouds will be negative charge, and this Earth gets polarized and becomes positive charge. And then you have these separations coming down in high concentrations. All right, so these are your separations. And then you got these positive charges going up. All right, so these are known as the streamers. All right, I just want to change color here because there's a bit of bullshittery that goes on here that I need to emphasize. I'm making it look really, really simple. And all right, so these are your streamers. Those are the positive charges coming out of the ground. And then we got the step leaders. Okay, this one is actually fairly accurate. So you got the step leaders. So what happens when they make connection? You end up getting a discharge, which is the opposite of an ionization that you're looking at. Streamers. Okay. The problem happens when the streamers from your body makes connection with these step leaders. Okay, you want to avoid that. And how do you avoid that? Glass is going to work just fine. All right, so if you put glass in between, what happens? The glass is going to get polarized, and that takes time. Okay, you don't want the streamers from your body become connected to the step leaders. You don't want that kind of connection, so you just want to sever that. All right, so that's the reason why you have to you just put a barrier between yourself and the step leaders. Okay, and something like glass would be perfectly fine for you to be able to sever that connection. Okay, this is kind of unrelated. This is something that we're going to keep going back to, though. Negative charges coming from the clouds. These are negative charge ions, or these are electrons coming from the clouds. That's what we got. So the bunch of them coming down. So it's these are going to be the step leaders that you're looking at. But I want you to remember. I want you to notice that the ground is positively charged because of polarization. These positive charges coming from the ground are ions. So the question is, where are we getting these ions from? And positive charges get pulled out of your body as well. So the question is, where are we getting these ions from? There's no explanation for it, guys. The ground being positive charged because of polarization is not the same as generating positive ions. There's no explanation as to how we get these, where we get these positive ions from. Okay, these are like mysteries. How would your body generate these streamers, for example? So that's a question mark. I have no idea. Somehow something happens. And then all of a sudden these positive ions get pulled out of your body. And then when these streamers start making connection with the step leaders from the clouds, obviously that's when you get struck by lightning. So the question is, how does your body generate these streamers? It's a question mark. All right. So the lightning is a fascinating phenomenon. All right, so Matthew, I'm going to give you 5 more points for that question. So that was an interesting discussion that you got started there. All right, so moving forward, does the strength of the electric field within a capacitor remain constant? There shouldn't be an or. All right, so does the strength of the electric field inside a capacitor remain constant? Okay, does the strength of the electric field change within a capacitor or remain constant? All right, that's the question that we will answer shortly. All right, we talked about the light, heat, as well as the sound with the lightning. So what causes the light? Quantum jumps, heat, random vibration, and rotational motion of the molecules. The sound is the sudden expansion and the collapse of the air, obviously. All right, so does the shape of the tip of the lightning rod matter? Okay, we'll take a look at it.